We've learned a great deal at this point about the nature of atoms and molecules and how atoms connect to form molecules and the like. In this set of videos, I want to turn our attention to a quantitative treatment of molecules and atoms and the topic of stoichiometry. We can think of stoichiometry as a kind of chemical algebra that allows us to translate from the world of mass and volume, which is the typical laboratory environment, to the world of numbers of molecules, which is more intuitive when we're starting to think about the molecular level. So let's begin by talking about the key concept really of stoichiometry, which is the mole. Essentially, the mole is a conversion factor from grams to atomic mass units, and we're going to see that in this video. If we think about the general problem of counting atoms and molecules, the big problem here is that atoms and molecules are extremely tiny and come in huge groups. This was, for example, what was so remarkable about Avogadro's achievement with Avogadro's law. He was able to count atoms and molecules to some degree, even though they come in massive groups. And we can ask the question, what counting unit for counting chunks of atoms and molecules is most convenient? Well, we express masses of substances in grams, but individual microscopic particles, atoms and molecules, are massed in atomic mass units. And so the most convenient counting unit to use would be one that would essentially convert between grams and atomic mass units. As an example that will get us to this number, let's consider counting carbon-12 atoms. Carbon-12 atoms have 6 protons in the nucleus and 6 neutrons. And one carbon atom weighs 12.00 atomic mass units by definition. This is essentially the internationally accepted definition of the atomic mass unit. That's a single carbon-12 atom has this mass. If we imagine we had a really sensitive balance, and there are other ways to get at this mass as well, we could determine the mass in grams of a single carbon-12 atom and determine that it would be about 1.99 times 10 to the negative 23rd grams. So we can now ask, how many particles does it take to add up to a mass of 12 grams? How many carbon-12 atoms do we need to get 12 grams? Well, to find this, all we really need to do is divide the 12 AMUs per particle by the 1.99 times 10 to the negative 23rd grams. This is going to give us a number of carbon-12 atoms such that their mass is 12.00 grams. When we do this division, we get 6.02 times 10 to the 23rd carbon-12 atoms, and you may recognize this as Avogadro's number. Avogadro's number is special because it's the number of particles in a sample, any sample, as we'll soon see, with a mass in grams equal to the mass of an individual particle of the substance in atomic mass units. So this means once we know the mass of a single particle, we can count molecules using Avogadro's number. Does this work only for carbon-12? Well, actually, no, it works for any element. And to see why, I want to use an argument that invokes micro and macroscopic masses and general variables. So consider two generic atoms, A and B, with a relative mass of Ma to Mb. So let's say, for example, that particle A is somewhat smaller than particle B, such that the mass ratio Ma to Mb is some number. What's the mass ratio of 2 atoms of A to 2 atoms of B? Well, if we take one atom of A and just add another atom to it, we get 2 atoms of A, and if we take 2 atoms of the larger B, we get something like this. And notice that the 2's cancel out. That's a critical piece of the picture here. We can cancel out the 2's on both sides of this ratio and see that, of course, the mass ratio overall is still Ma to Mb. It's the same mass ratio even though we've gone from 1 particle of each to 2 particles of each. We could continue this idea for 3 A atoms and 3 B atoms, and we would see again that the overall mass ratio is still Ma to Mb. This works for any number of A and B atoms, of course. We could extend the argument to as large a number of atoms as we wanted. What that means is the mass ratio of Any particular number, let's take Avogadro's number of A and B atoms, is still m sub A to m sub B. That's the ratio of their microscopic atomic masses, right? That's the mass ratio of one particle of A to one particle of B. What this means is that we can use the ratio of masses at the atomic level, in other words, the relative atomic masses, to reason about the relative masses of a mole of substance for any particle, atom, molecule, what have you. And so our means to count microscopic particles is the mole. And we can say that for all atoms and molecules, a sample with a mass in grams equal to the mass of a single particle in AMU contains Avogadro's number of particles. That's essentially the definition of Na, right, as we saw before. It's the number of particles that adds up to a mass in grams equal to the numerical mass of a single particle in AMU. Such a sample is called a mole of substance. Every mole of substance contains Avogadro's number of particles, and the mass in grams of a mole is equal numerically to the mass of a single particle of a substance in AMU. So let's go back briefly to carbon-12. We know that a single atom of carbon-12 has a mass of 12.00 AMU by definition, right? But if we take a pile of carbon-12 atoms, let's say, that weighs 12.00 grams, we know immediately that the number of particles in this sample is Avogadro's number, n sub A. And so what we can say for carbon-12 is that carbon-12 is characterized by a molar mass of 12.00 grams per mole. And that's numerically equal to the mass of a single particle in AMU, and this will always be the case. What that means is that we can literally read the molar mass for the elements, for atoms of the elements, right off of the periodic table, because the relative atomic masses, which, if you think of carbon at 12.00 AMU as the standard, those relative atomic masses are the masses of the atoms in AMU, right? And so we can read those directly just by changing the units as the grams per mole of each element. And so now, with this in hand, we can now use mass, particularly in grams, to count number of particles. And that's a very powerful ability because we can go from the laboratory world of mass and volume to the chemical or molecular world of counting particles. So let's practice this skill of determining molar mass from a molecular formula. And I've chosen deliberately an example of a molecule that's fairly large so that we can see how this process works. The idea is to add up the average atomic masses of all of the atoms in the molecule and then add grams per mole units at the end of it. Simple as that. We use the average atomic masses because we're assuming that this is a natural sample of material whose atoms reflect the isotopic abundances of all the elements within and all that good stuff. So the example here is chlorophyll A, and it's C55, H72, Mg, N4O5. So quite a few elements in this thing. The idea is to first list the individual average atomic masses for the elements within. So for carbon, we can list that average atomic mass per atom as 12.01. Hydrogen is 1.008. Magnesium is 24.3. Nitrogen is 14. And oxygen is 16. So now we take each of those average atomic masses for the individual elements and multiply them by the number of atoms present within the molecule. 55 times 12.01 plus 72 times 1.008 for hydrogen plus 24.3 times 1 magnesium atom plus 4 times 14 for nitrogen, and finally plus 5 times 16 for oxygen. And when we do this, we get an overall molar mass of 893.4 grams per mole.